right? Okay, so hopefully that kind of makes a bit of sense, okay? But I just want to sort of talk a little bit more about what the confidence level actually means, okay? I've kind of hinted to it, but I just want to sort of explicitly point out this is what a confidence level actually is, okay? So I want to say a confidence level is how many samples, so if I carry on taking samples, okay, how many samples will contain the mean on average? Okay, so if I take a confidence level of 95%, what that means is that if I was going to go out and take 100 samples, okay, I would expect that 95 of those samples, which I collect, will contain the true population mean on average. So it will contain the true population mean on average. Now, just to kind of illustrate that a little bit, I've got a lovely little GeoGebra applet which I just want to show you, okay, over here. So I've got a lovely little GeoGebra applet which I can show you, okay. So here I've set the confidence level to different values. So let's just, for example, set the confidence level to here, 0.95. Okay. Now what you can see here, and you might be able to pick this up, you might not. Okay. What you can see here, everything in green. So I've got 100 different samples which I've taken, and I've constructed a confidence interval for each of the different samples. So you can see the blue dot is each of the different sample means, and then I've sort of formed my confidence interval around that each of those sample means. Now the true sample mean is down here in pink, down the middle, and you can see that out of the 100, 95 of them contain the true population mean. So for example, if you just look at the top one, you can see the bar extends from here all the way over to here, and you can see that true population mean falls within that interval there. But you can see the ones in red, for example, that one, that one, that one. So some of them don't contain the true population mean. And on average, if I take 100 samples, I would expect 5 of the intervals which I construct will not contain the true population mean. So they will not contain the true population mean. And likewise, you can see that as I change the confidence level, okay, so if I reduce the confidence level down to 50%, what that means is that only half of the samples, half of the confidence intervals that I produce will contain the true population mean. Okay, but you can see as a result, as I reduce the confidence level, you can see that the size of the bars, the intervals, if you like, are getting smaller and smaller and smaller. And you can see that. You can see that as I increase them, okay, the confidence intervals obviously get larger. Okay, so as I decrease the confidence level, because I'm less confident about containing the true population mean now, it means that the interval is much, much smaller, which means only half of the samples which I collect and the intervals which I form from those samples will contain the true population mean. Likewise, if I sort of ramp this up to 95%, and if I change n, you can see that that will also change. So if I reduce n, you can see that my confidence intervals now are much, much longer. Whereas if I increase n, you can see that the confidence intervals which I form are now much, much smaller. Okay, so it's this idea that I am trying to form some interval, that's literally what they're saying, such that I can be this level of confidence. And 95% confident means I'm 95% confident that the true sample, the true population mean, will be within the confidence interval that I construct. Okay, so hopefully that kind of makes sense. Really, it's a kind of a balancing act. The two things that you need to balance are the confidence level, okay, the confidence level, and also n, the number of samples. Because obviously, as you increase n will go down, okay? Likewise, as you increase the confidence level, then that will go up, so n will go up. Okay, so if you increase the confidence level, it means you can be more confident that the true sample mean is going to lie within the interval which you form. Okay, so that's x bar, and that's plus m, and that's minus m. You can be more confident that the true population mean is going to lie somewhere in there. However, you're only more confident because you've made the interval larger. Okay, whereas if you decrease the confidence interval, so increase the confidence level, it means that the confidence interval is going to get smaller, but you're going to be less confident that the true population mean is going to lie in that region there. Okay, so hopefully that kind of makes sense. Now I just kind of want to finish off on an example. Okay, so let's suppose we take 100 samples, okay, And we know that when we look at all 100 samples, the mean of those 100 samples comes out as 50. And it's known from previous kind of experiments that it should be the case that the population standard deviation is equal to 3. Okay, so this is already known, this is given, we know that this is definitely certain. But from experimenting, we've worked out that if we take 100 samples and then take the mean of those 100 samples, we get the sample mean is 50. We want to construct a 99%, so we change the confidence level now, we want to be more confident. So as a result, we're then increasing the confidence interval. 99% confidence interval, and this is a symmetric confidence interval, by the way. Okay, so we want the same number of data on the left as we do on the right, just with an ordinary normal curve, same number of data on the left and the right. Okay, so we will construct a 99% confidence interval for the true population mean, okay, for mu. So this is how we do it. Okay, we know that if we want 99%, okay, this x bar that we've got here, this 50, okay, if we move some margin above and some margin below, the true population mean should lie within this interval, as long as we look at 99% of the data. So we should expect 99% of this data should lie within some given interval of the true population mean. Okay, so I think it's going to be helpful here to draw out a little normal curve for us. Okay, so we know here is the sample mean at the moment, so this is 50. Okay, we want to look at what value over here and over here will mean that the area in the middle, okay, so this is plus m and sort of minus m if you like, okay, what value will give us 99% of our data? So what value here and what value here will give us 99% of our data? Well, if you think about it, area underneath the curve, that's got to add up to 100, which means I've got to split the remaining 1% equally each side, because of course it's symmetric. So I'm expecting 1% in here, sorry, 0.5% in here, and 0.5% in here, because of course I'm splitting the remaining 1% equally, so 0.5% over here, 0.5% over here. So then if I look in my tables, okay, I just need to look, and of course make sure you're looking at the negative side, because of course tables are cumulative, so I'm just going to look at 0.005, that's what I'm looking for. 0.5% is 0.005. That's what I'm looking for in the table. So I'm looking over here, can I find 0.005? Okay, so 0.005, where are we? It's going to be in here, you see, so it's kind of split between these two values. So I'm just going to choose one of them. I'm just going to choose negative 2.57, but you could have equally chosen negative 2.58. Okay, so I'm going to choose negative 2.57. That is the value, so negative 2.57, and because this thing is symmetric, I know that 2.57 should be over here. So remember, this is the number of standard deviations above and below the mean that I need to look at in order to get 99% of my data. To be 99% confident that mu, the true population mean, lies within this interval which I've constructed. Okay? So let's have a look at this. First things first, I need to have a look at the sigma over root n value, because of course I know that when I take the mean of these samples, so at the moment x is distributed with some mean, okay, and the standard deviation is going to be 3 squared over 3 squared. Okay, so I'm just looking at one of them. Okay, but when I take the mean of those 100 samples, I know that it's going to be normally distributed with, again, some unknown mean. That's what I want to find, but it's going to be 3 squared divided by 100. That's now my variance. Okay, so this is just 1. Okay, this is if I put together 100 samples. Okay, so therefore if I want to find m, I just simply need to say, well look, I know that if I look at 2.57 standard deviations above and below the mean, that I should have 99% of my data. So it's going to be 2.57 times by my standard deviation, which is going to be 3 over the square root of 100. So just the square root of this thing. Okay, that should be my m. Okay. Now, by the way, this thing here is not strictly speaking the standard deviation. It's actually called the standard error, because I'm looking at how likely values are, so how likely my intervals are to contain the true population mean, I call it the standard error. It works in the same way as standard deviation, but because I'm looking at it from a slightly different perspective, I'm looking at it from the perspective of finding the true population mean, it's actually called the standard error. And this is how we calculate it. It's just sigma over root n. Okay? So therefore that's m. So I can construct my confidence interval now. So I'm going to put mu in the middle. Okay? I've got x bar, which is 50. And on the left-hand side, I've got to take away m. Well, if that's m, I've got to take away 2.57 standard deviations, and the standard deviations are worth 3 over root 100. Or the standard error is 3 over root 100. And if I look at the right-hand side, so my upper confidence interval, I'm going to take my mean, which is 50, and I'm going to add on m. So I'm going to add on 2.57 standard deviations, where each standard deviation, or standard error, is 3 over root of 100. Now if I actually calculate that left-hand side, so I stick all of that left-hand side into the calculator, the lower confidence interval, that comes back as 49.229, okay? So I've got the mean, the lower bound of the mean is 49.229. The upper confidence interval, the upper bound if you like, if you stick that into your calculator, you get 50.779. So in other words, I know with 99% accuracy or 99% confidence that the true population mean for this particular sample should lie somewhere between 49.229 and 50.779. Okay, so if I plot this on a number line to make it a little bit clearer, there's 49.229. There's 50.779. This is just on a number line. I know that my true population mean should lie within there. I'm 99% certain that given these particular parameters, so based on 100 samples, where the mean of those 100 samples was 50, and I knew that the standard deviation was 3, I can say with 99% accuracy that the true population mean should lie between 49.229 and 50.779.